This is the next video in the chapter on chemical bonding and molecular geometry. We have just learned about our first tool for predicting which of two legal structures it might be, which was formal charge, and now we're going to learn about the second tool for predicting the most likely structure, which is called resonance. So I've gone ahead and drawn two possible Lewis structures for NO2 minus, one with a single and a double bond, and one with a double and a single bond between those oxygens. So let's go ahead and try out the first tool that we used, the formal charge, to try and predict which one of these structures would be preferable. So these oxygens are different. So I'm going to call them oxygen A and oxygen B. So for oxygen A, we have 6 valence electrons, minus 1, 2, 3, 4, 5, 6 lone pair electrons, minus 1 bond is a formal charge of minus 1. Nitrogen has 5 valence electrons, minus 2 lone pair electrons, minus 1, 2, 3 bonds is a formal charge of 0. For oxygen B, we start with 6 valence electrons. We subtract out 2, 4 lone pair electrons and 1, 2 bonds. Formal charge of 0. We'll add those formal charges at the top. So we had -1, 0, and 0. And we also want to make sure that the sum of all the charges equals the charge of the molecule. So -1 plus 0 plus 0 should equal a charge of -1, and that is true. So those are legal formal charges, and they're looking pretty good. We only have one non-zero number. So let's try this structure. We'll call the left one oxygen A and the right one oxygen B. So oxygen A has 6 electrons. It has 2, 4 lone pair electrons. It has 1, 2 bonds. So it has a formal charge of 0. The nitrogen, we start with 5 valence electrons. We subtract out 2 lone pair electrons and 1, 2, 3 bonds. So it still has a formal charge of 0. And for oxygen B, we start with 6 valence electrons. We subtract out 2, 4, 6 lone pair electrons and 1 bond, giving us a formal charge of -1. We've got 0, 0, -1. And if we add those together, they equal -1, which is the overall charge. So now we can say to ourselves, which one of these would be the better structure? We can see that they are essentially the same structure. They each have 2 zeros and a -1. And in both cases, the -1 lives on an oxygen, which is more electronegative than nitrogen. So that is a good place for it to live. So what we see here is these two options are actually equally good. They're essentially the same structure. They're the mirror image of each other. One of them has the negative charge on the left side. One of them has the negative charge on the right side. But the orientation of the atoms is the same. And so if this is true, we hope that experimentally we can determine some proof that proves this. So one of the things we can do with X-ray diffraction is we can see that stronger bonds have shorter bond lengths, the distance between the two atoms. So if we look at the bond lengths, we can use that to help tell us where the single bonds are and where the double bonds are. So if we're looking at nitrogen-oxygen bonds, we would expect each of these molecules to have one nitrogen-oxygen single bond that was rather long and one nitrogen-oxygen double bond that was rather short. So we would expect to measure, two different bond lengths for NO. A longer one and a shorter one. So, update reality. When we do the experiment for the XRD, we are surprised to find this is not what we see. So experiments show only one NO bond length. No matter how many of these molecules we measure, we only find one NO bond length for all of them. So that means that this NO bond and this NO bond are the same length, so they must have the same number of electrons shared between them. Well, that doesn't work with the picture that we drew. So maybe we could try and redraw it. Maybe we could redraw the Lewis structure in a way that makes those two bonds equivalent. We could do something like this: 2, 4, 6, 8, 10, 12, 14, 16, 18 with a negative charge. So let's check our octets first in the structure that we've made. 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for this oxygen, 2, 4, 6. Uh-oh. That is not a complete octet for nitrogen. So we already don't like this structure very much because it's illegal, because it has an incomplete octet. But just to really drive home the point, let's go ahead and check out the formal charge. Formal charge for oxygen is 6 minus 2, 4, 6, 7 is minus 1. 5 minus 2, 3, 4 is positive 1. And 6 minus 2, 4, 6, 7 is minus 1. With minus 1 plus positive 1 plus negative 1 equals a total of negative 1. So we don't really like this either, because I'm seeing oxygen as the more electronegative element. It has a minus 1 and a minus 1. Nitrogen as the less electronegative atom with a positive 1. That's okay, but these are three different formal charges that aren't 0, compared to these structures where 2 of them were 0 and 1 of them was 1. So technically, this structure that I've drawn does have equivalent NO bond lengths, but it has really high formal charges, and nitrogen has an incomplete octet. So that is not the answer. So now what are we going to do? How can we justify our experimental evidence with these Lewis structures that we happen to like an awful lot? The answer here is resonance. So resonance indicates when you have two or more Lewis structures which are equally good, the most correct Lewis structure to represent what it really looks like experimentally is an average of all of the possible options, or rather an average of all the legal options. So in the case of NO, we had two equivalent options. They were both equally good, so the most correct way to write the Lewis structure is to write both of them. But we need to write it in a particular way to indicate that this is a resonance situation. So we'll write them really quickly down here. So the way that we indicate that these two structures are equally good is we put this double-sided resonance arrow. So we only use this when drawing Lewis structures that are equivalent. And what this resonance arrow means is that you need to draw both of these structures to accurately represent where the electrons are in these bonds. So let's talk about what that arrow means and what that arrow does not mean. So what that arrow does not mean is that the electrons flip back and forth between those two orientations. This is not a chameleon that changes color and is sometimes blue and sometimes green. No, both of these are true all the time. We just need both of them to represent the one state this molecule is always in. So there's one state, and that one state is the average of both options. And so to represent what it is an average of, we draw the two structures with a resonance arrow in between. The other way to draw it without the resonance arrow is to try and draw one picture that's an average of both of those pictures. So we can think of the bond length as being an average between a bond length of 1, a single bond, and a bond length of 2, a double bond. So an average of 1 and 2 is around 1.5. So sometimes you'll see your textbook draw each of these bonds as being 1.5 bonds with one solid line and one dashed line. So this would be the way you could represent the structure with a single Lewis structure. But it isn't very helpful because sometimes these bonds are 1.5 bond, and for other molecules, they might be 1 1/3 bond length, and there's only so much information you can give in a dashed line. So this is the more correct way to indicate it, to draw all of the possible resonance structures, not forgetting to include the charge and the double-sided arrow. So resonance is something you will see more as you move on through the introductory series into organic chemistry. There are many resonance structures in those classes. So we still need to talk about exceptions to the octet rule in the next video.